so yesterday we saw one of the first key ideas in parabolic dynamics, so mixing via shearing. So shearing and how to use it to implement a boost from ergodicity, unique ergodicity to mixing. And today we will see another example of this in a different setting where the shear is much less strong and harder to get. So we'll see time changes of Eisenberg Nil flows. I will start slowly with some background. But first I want to add a few references. I want to have a little appendix from yesterday's talks. So I wanted to add a few comments about yesterday before we move to Nil flows. And the comments were, first of all, I think I said it, but maybe I didn't stress it enough. So I presented a sketch just of my proof with Forney of mixing of type changes of the horocycle flow. But the point of our proof is really to have quantitative bounds, because if you just want mixing, actually Marcus' setting does cover time changes. But because there was some question at the end about variable curvature, maybe I wanted to tell you what is the setting of Marcus. So again, he considers this an also flow and a flow on a stable, one-dimensional stable or unstable leaf of a codimension 1 and also flow. And crucial for him is always this commutation relation. So I still call the flows G and H, even though here this could be an also flow, and this is the flow we want to study. So that there should be a commutation relation similar to what we saw yesterday. Yesterday here we had e to the ts, and in general, okay, you can take indeed this Margulis parametrization, which is expanding, and then you will have a relation of this. So this is somehow the key function that tells you the correspondence between the expanded and, so it tells you the shear. So this function encodes information about the shear. So and Marcus' assumption, so his setting is that you have such a relation, and that a star such that the partial second derivative exists and it's continuous. So you want this smoothness exists and is continuous. And then maybe you can tell me where it fits and how it's rare, right? So he actually has some discussion about non-smoothness, and so it covers some negative variable, but it's very special. So I'm understanding. Yeah? Okay, then this was just for answering some question at the end. And then I wanted to say something else that I haven't said. So, and also before Marcus, there is also a previous result on time changes. This is also very old. This is Kushnirenko. And he already proved mixing, again, nothing of this is quantitative, but it's mixing of smooth time changes, but with an additional condition. So I'm using the notation from yesterday. So we have alpha, which is the generator of the time change. So H alpha, I'm using the notation from yesterday. Under the assumption that, assuming, it's knowing that I have, okay, I got to the new board, assuming the following condition, that x alpha over alpha, so again, this is the derivative in the geodesic direction, in infinity norm is less than 1. So this is some small time change which doesn't move too much. So it's, on one hand, it's much more restrictive. So Marcus, and then the quantitative version and the spectral version that we have is for every smooth time change, and here we have a smallness condition. But it has an advantage that actually, so we consider co-compact case yesterday, and it covers also gamma lattice, also when the volume is finite, but not necessarily compact, and there are cusps. And this is called, actually, let me give it a name. Let me call it KC for Kushnirenko condition. So Kushnirenko condition, okay, we understand. And this condition, okay, so this I wanted to say for past results, and then contemporary and 2 hours and future. So, yeah, maybe I wanted to say this, that it is actually open. So if we, it's open in the case of a finite volume. So if you have a lattice, so maybe a question. So if you have, I forgot where I quotient yesterday. Okay, X most gamma, finite volume. Open, so question, are all smooth time changes mixing? So this is not clear. So because again, we have this condition, but it seems that it's, I mean, maybe yes, but it seems that it really plays a role. And actually, sometimes I even try to think whether one can destroy mixing. So one can actually use high oscillations in the cusp. And so it's not clear. And maybe it's really necessary to have an assumption in the non-co-compact case. And the other thing I wanted to say, some more younger, well, new generation and continuation of our trend. So first of all, I mentioned that we proved also spectral information. So the spectrum is absolutely continuous and Lebesgue. I don't want to talk about this now. And maybe if I have time, I'll talk you towards the end of last week. But let me mention that at the same time that our paper with Giovanni on the spectral question, Piedra de Aldecoa, actually I don't know how you pronounce his name properly. So he also proved at the same time, not a Lebesgue, but AC spectrum for time changes of the, and in this case it's also lattice, but with Kushnirenko condition. So he uses a very different method. He doesn't using this mixing via shearing, but more function analytic more method. And it does give, maybe I write here because then today I can, then we will change to a new topic. And then the newer generalization of our work, this is, I want to mention 2 results. So first of all, so Lucia Simonelli, and maybe I also want to work Davide Ravotti work. So Lucia was a PhD student of Giovanni, and Davide was a PhD student, my PhD student in Bristol. And they both pushed our method with Giovanni, and they also considered some higher rank. So they went to the setting of a semi-simple Lie group with finite center. And then you can look, again, lattice, and G mod gamma, finite volume. Okay, I already said lattice. And nilpotent element. Nilpotent flow, so the adjoint nilpotent. Okay, and they proved in this setting. So Lucia actually has, maybe I should have done 1 and 2. So this is the setting in both. And somehow you can exploit if you are, even if you are in this setting, you can still find a copy of SL2R inside your semi-simple group. So you can still couple this nilpotent with some X that will give you the important commutation relation. So you're still playing in SL2 even though you are, but they could, so Lucia could prove the spectral result that we have. So she could prove, I think it's, so AC spectrum, okay, it doesn't matter. This is more to be AC spectrum when under the with the Kushnirenko condition, and the Lebesgue spectrum for the co-compact. And actually I said, no, she generalizes both because she generalizes Piedra work and our work respectively. And Davide could prove quantitative estimates. So he proves quantitative mixing estimates in this setting. And again, the proof is very much mixing via shearing and these estimates that we saw yesterday, but the input, he has to work in L2, so modify a bit the estimates. And yesterday I thought we have some quite fine information about equidistribution of arcs in the flow direction by Buffetov and Forney. So Buffetov and Forney is our quantitative input, and he uses more classical decay of matrix coefficients as a quantitative input. And maybe I mention one last, and there is also one work of Ravotti, Kanigovsky, Adam Kanigovsky, and Ravotti. And they prove, in the setting of the horocycle, they prove horocycle time changes. They prove also quantitative tree mixing. But there is some, okay, now I didn't check exactly all the assumptions, but okay. I think they have also some result on higher order mixing, but only when the time change, there is some hypothesis on the on the discrete series of the, okay, doesn't matter. Okay, this is all. So I wanted to say that this has been actively already, there is still open questions, as you can see, and it's not all done, but there has been continuation of activity extending this type of ideas and techniques to unipotent flows, for example. Okay, and now I want to change. So for people who are new in the audience, I'm going to start a new topic, and also some students maybe. So we'll have a first hour a bit, again, slower with some background in the topic of Heisenberg Nil flows. And as I said, the horocycle was somehow the best parabolic flow in the sense of uniform shearing. And here, this will be an example of a flow which is not, it's only partially parabolic, so it doesn't really have, yeah, so we'll see. But we can still perturb it to uncover the parabolic features. Okay, so background. So we start with the Heisenberg group, and you can think of it very concretely. I'll try to be concrete today. You can think of it as upper triangular matrices with real entries. And, okay, let me write the generators of the Lie algebra. So, okay, so you have these matrices 0, 1, 0, 0, 0, 0, y, 0, 0, 0, 0, 1, 0, 0, 1, sorry. And z, let's put it here, 0, 0, 1, 0, 0, 0, 0, 0, 0. So if you exponentiate them, then, okay, they give you one. Okay, no, let me just. So these are the generator of the algebra, and they satisfy the famous, well, Eisenberg relations. So x and y, if you take the commutator, and you can just really take matrix multiplication and take the commutator xy minus yx, this will give you z. And on the other hand, x and z and y and z, the commutator is 0. So x and z commute, and y and z commute. And you can really just verify these relations if you want. And, okay, so this is the Heisenberg group and the Heisenberg relations. And I'm going to take a quotient of the Heisenberg group. So maybe let me, okay, I will take gamma discrete subgroup. And maybe just keep in mind a very precise example. You can just think of taking gamma, the set of the same matrices of the same form, just with integer entries. Okay? And I will assume that, so, okay, and I want to look at x, which is the quotient. And now, okay, so today the quotient on the left, just for consistent with the paper. And I want this to be compact. So, okay, in this case, it's compact. It's actually like a T3, like a three-dimensional torus. And we call this compact Eisenberg Nil manifold.
Excuse me, the element of the diagonals are all ones.
Sorry, of course. This is the typo. Thank you. Sorry, why there is an extra zero? I don't know. Of course. Thank you. Okay, very good. Absolutely. No, I don't know. There were too many zeros. I got lost in the number of zeros. No, of course. Diagonal is 1, and it's upper triangular with diagonal 1. All of them. And actually, how am I doing with boards? I need the... this time we try like this. So we push this up. And we push the second up. And we should have a third. The third I already used. Okay, but the third I can erase because we already moved away from horocycle and time changes of unipotent. Okay, so yeah, what I want to say, this restriction, this lattice, it's really not far from the general case because actually you can show, maybe I put it on a corner because it's not so important. As a fact, if you have your lattice up to automorphism, actually you can show that there exists an integer, E, such that gamma, you can bring it in the form 1 x z over E, 0, 1, y, 0, 0, 1. Yeah. So it's essentially just almost a general case. So we'll stick to the integer. E is equal to 1 case. Okay. And then we have that, so H acts, Heisenberg group, acts on X, my Eisenberg Nil manifold, by, so I quotient on the right or on the left? By right multiplication. Okay. And again, so I have an action, and I want to take again the Haar measure, mu on the quotient. So mu Haar measure, mu induced by Haar measure on the quotient. On the quotient. So, okay. And so what is Nil Flow? So Nil Flow, in this case, Heisenberg Nil Flow, but it's in general, Nil Flow, you just don't start from Heisenberg group, but start from nilpotently group. So a Nil Flow, in this case, Heisenberg Nil Flow, is just action of one parameter subgroup. So you take one parameter subgroup action. So you take one parameter subgroup of H and you act on your Nil manifold by multiplication. So I'm just going to write, so you take some omega. So and in general, I will introduce some notation. I will write components A, B, and C. So I take some omega in the Lie algebra. It's A, B, and C are coefficient in X, Y, and Z. And so, and I will denote it phi R omega. So omega is to remember the generator. This is my notation for flow. So it's a one parameter family. And this is just, so from x to x, I take x as a class, and I multiply by x t omega. So this is the one parameter flow obtaining exponentiating omega. Okay, so I want to say that I will give a very concrete description, which is not in coordinates and in special flow very soon. So okay, for now, okay, we don't need to understand more. Where am I in boards management? I think I need to, I will use the lab. Maybe I'll start here, but I think it's okay. Okay, so what are classical results? What do we know about? So these Nil flows have been studied a lot, and the initial results go back to the 60s even. So classical result so this is, let me put a reference, Auslander, Green, and Hahn. And we are, I even put 1963, we are quite far back. So they studied ergodicity and the unique ergodicity of these Nil flows. Yeah, I have, okay. And so we proved that phi r omega is uniquely ergodic. I recall you, uniquely ergodic means that every trajectory is equidistributed with respect to mu, as we wrote in the first day class. So it's uniquely ergodic if and only if it is ergodic. So first of all, when you have ergodicity, you already have automatically also unique ergodicity. And if and only if it is minimal. Minimal means that every orbit is a topological notion. So all orbits are dense. So once orbits are dense, they automatically are equidistributed. And OK, this is not interesting, but not very concrete. And if and only if, for example, A and B are rationally independent. This is more concrete. A and B are A, B, and 1 are rationally independent. Independent over Q. So that means that if I have a linear combination, Ka plus Lb plus n is equal to 0, where K, L, and N are integers, yes, then they have to be 0. OK. So maybe I'll give you some bit of motivation for this. No, not a proof, but so as related to a Nil flow, as an Eisenberg Nil flow, there is also a flow on the torus. So maybe I'll let it here. So maybe remark. OK, in any case, this result gives us understanding of ergodicity, unique ergodicity. So we understand unique ergodicity. Remark, so I can take the abelianization. So I can take, and again, maybe I'm confused what I'm quotienting. OK. If I quotient by the commutators, I get something abelian, which is, I was using H. Sorry. Am I using H, right? Yeah, sorry, this is H. Because it's Heisenberg and not any nilpotent. So this is an R2. And you can project the lattice. So you can take gamma modulo commutators. And in our case, this is some kind of Z2. And the quotient is at T2 is a two-dimensional torus. And you have a projection from X to this torus. And under the projection, phi omega, now I'm using omega on top, projects to what is called a linear flow on this torus. So projects to omega t bar, which sends xy. So I'm using coordinate xy. And it sends it to x plus at, y plus bt. And a and b are our coordinates. So you see that this is a necessary condition. So, okay, you see if you know a bit of dynamical system, but if you have irrational lines on, this is a torus, it's a square, with, and these are irrational lines of slope b over a. So they're going to be dense, and actually it will be uniquely ergodic. So this is going to be uniquely no, something I'm doing wrong. No, okay, I'm doing something. Okay, so this will, I need that these two are irrational in order to have. And then we know that, then it's essentially Furstenberg who proved that you can actually lift, under this condition, you can actually also prove unique ergodicity for the, okay, so maybe that's enough for background. And what I want to show you now, so claim that I'm going to prove. I not call it proposition because it's not really, we'll just see it soon. But I want to show you that actually this flow, okay, it's uniquely ergodic, but is never mixing. So it really fails mixing drastically. And I want to convince you of this. And to do this, we want to give it a very concrete representation as a special flow over a skew shift. So what I want to do, maybe recall you first. Okay, so maybe I should change board, because otherwise I'll be stuck with this board forever. Okay, so I want to consider a Poincaré session. So again, I know not everybody has dynamics background, so when I erase the board, so this is a continuous flow on this three-dimensional space. And I'm going to take a surface, which is transverse to my flow, and look at the map, discrete map, that I get when I wait for my flow to come back to this surface. So this is called the Poincaré map. And we'll find a very explicit expression for the Poincaré map and recover the flow as a suspension over this map. Okay, so that's what I want to.
You have said that this three-dimensional flow has a quotient which is a two-dimensional constant.
So, 1 second. So, a very important thing, I don't want, so there is this underlying T2 torus, but I don't want to use that. So I wanted to, so this is a very good point. So you could maybe tempted to, okay, say, okay, I already said that there is this abelianized torus, and I have the projects on a irrational flow. But that will not help me to anything I do today. I need to find another tilted section instead. And so this is a projection somehow on x and y. And I want somehow to project on x and z or y and z. We'll see why. Okay. Okay, so first I change board. So I have the map that I want to find is skew shift. So let me just define. So fix alpha and beta real. And then f. So it's f of alpha beta. It's the map from T2 to T2. So from torus to torus. And this is just a map x. OK, I have a problem. I will still call them x and y. But there will be some x and z. OK, we'll deal with this. It's not the same. It's not going to be the same y that I have there. But OK, so this is just an abstract definition. So I have T2, so it's x plus alpha mod 1, and y plus x plus beta mod 1. OK. OK, so this part is just, it's called a rotation by alpha, x plus alpha mod 1. And of this map, we know everything. It's the linear elliptic simplest map. And so in particular, it's uniquely ergodic when alpha is irrational. So maybe I'll write it. For alpha irrational, R alpha as a map of the torus, or T to T, is uniquely ergodic. This is very, very old result by Weil, and one of the first that one proves in every ergodic theory class. And Furstenberg is the one who considered the Skew products. And I think we are, I didn't put the year, but I think we are again in the 60s. 60s? Do you know the year? Yes. He proves that again, if alpha is irrational, then actually f alpha beta is also uniquely ergodic. And this is really one of the first and most important examples of unique ergodicity and the foundation of ergodic theory. OK, so, and maybe this is unrelated to today's talk, but maybe it's good to make a connection. So let's take for a second beta is equal to 0. Beta plays essentially no role. It's just a shift in this coordinate. You can just study the case where b is equal to 0. And then this is exercise in very basic, not even ergodic theory class. Just to compute the iterates of this map. And you can just check by induction, if you want, that you get orbits of the rotation. So this is x plus n alpha mod 1. So sorry, I didn't say, but this map is what is called a skew product or an extension. So the x-coordinate play by itself. So the x-coordinate is just playing by itself, and the y-coordinate plays with x and y. So it's called an extension because so it's called an extension in the sense that on the two torus, so if this is x and this is y, here I am applying the map R alpha. And you can think it's a map that kind of fibers over the base dynamics. So extension, so fibers, so there are vertical fibers are preserved in the sense that and exchanged, so not preserved, preserves as vertical fibers. So a vertical slice goes to a vertical slice, and the slice over x goes to the slice over x plus alpha, and exchanged by dynamics of R alpha on the base. So this is called the skew product dynamics. So the transformation R alpha maps on the base and determines how the vertical bands, the vertical slices exchange. And in each vertical slice, if I fix x and I look what happens to y, maybe I'll write this because we'll use it later today. So it's good to, if you haven't seen it. So for fix, so let me call it I on x. So maybe I should write it here. Sorry. So I want to write that so x cross 0, 1 is mapped to R alpha of x cross 0, 1. And on this, the map is a translation. So on this, and now I run out of space. On this, sorry, I finish here. On this, we have y goes to rxy. I'm doing, if you want, the beta is equal to 0, or if you want, mod 1. Okay, so I have a rotation in the fiber. So in particular, remark, it's isometric in the fiber. Okay, and I just wanted to finish here the formula that you can compute explicitly the iterates, and this is r alpha n of x. The first coordinate we understand play by itself, and the second, I hope I wrote it right, it's n square alpha plus n minus 1 divided by 2 x. And what I wanted to say that this n square alpha is a very much studied sequence in number theory and combinatorics. Actually, I saw that the first Hadamard lecture series was given by Ben Green, right? And he talked about Nil sequences and okay. So, for example, this is important also in number theory. Yeah. So, for example, if you want to prove that n square alpha is equidistributed modulo 1, so if I fix irrational alpha and I look at n square alpha for n integer, this fills the unit interval uniformly with respect to Lebesgue measure. You can use this Fusterberg skew product and use it. It's uniquely ergodic. It's exactly. And actually, okay, this connection, I will not go back to it, but to mention, there is this connection between Nil flows, Eisenberg Nil flows, and exponential sums, and this n square alpha. So Forni and Flaminio and Forni have proven quantitative results about equidistribution of Heisenberg Nil flows. So they can prove make this equidistribution effective. And maybe I'll mention something next week if I want to do. Okay, and they also can get many number theorists works on bounds and exponential sums, and Flaminio and Forni have pushed this more dynamical approach, that if you study Heisenberg Nil flows, you can get, actually using ergodic theory, you can get quite good bounds, and not only for, in general for observables over Nil flows. And so in the number theoretical point of view, some results by Trevor Woolley, and maybe I'm forgetting many other people, and somehow actually Flaminio and Forni essentially can match best technology of number theory in terms of ergodic theory. So this is just a digression. Okay, let's go back to say ergodic theory is powerful as much as number theory. Okay, so how are we doing? Oh, we are doing plenty of time. Okay, so now then, little lemma. Why did I introduce these Q products? And because they appear as Poincare maps on Nil flows. So let's take phi r omega uniquely ergodic. So we know by the previous theorem when this happens. Heisenberg Nil flow. And I claim that we can find a section, so sigma, it's a hypersurface. It's actually going to be a T2. So, actually, let me just write. There exists a torus, T2 torus, contained in X. X is my Heisenberg manifold. So again, you should imagine I have this three-dimensional space, and inside I have this two-dimensional thing, and I can take my flow and wait until it comes back to the section, such that the Poincaré map P from sigma to sigma, the Poincaré first return map given by, you take a point in your section. You take a point in your section. I think we have too many x because my space is x, but my surface is going to be two-dimensional. It's OK. We'll not so good. So OK. So first of all, abstractly, so I have an element. Let's call it G then. So we have G maps to PG. PG is the flow. So I have a point, I call it G now, and G is here. And the PG is the first return. So it's a phi omega of return time of G, where Rg is the minimum t greater than 0, such that phi omega t of G belongs to sigma. Sorry, I didn't plan to define Poincaré map, but I realized that not everybody is a dynamicist, so to me it's so obvious that I don't need to define Poincaré map. OK, but so let me explain in words. I take my point on the section, I flow, I look at phi t omega G. This is the forward trajectory. And it's minimal, because we said uniquely ergodic is equivalent to minimal. So I wait. The orbit will be dense. So I will come back close to G and intersect the section again. And this point is the first return. OK, but this is not the lemma. The lemma says uniquely ergodic. And the Poincaré map, this is the general definition of Poincaré map, is of the form. No, let me just write, and we compute it in the proof. Is phi alpha f alpha beta. It's one of these Furstenberg skew products for some alpha and beta. That will depend on A, B, and C. And maybe I want to sketch this, so we have time, and good to build some background. OK. So let me give the proof. And also, again, it's not the same torus that we had before, because on that torus we had projected to a linear flow. So here, the section will be the following. So I will take, as generators, I will take, yeah, maybe I should have said first. So it's uniquely ergodic. So no, it's OK. Whatever choice I make is fine. I can choose either x and z, or I can choose y and z. This is irrational, so one of the two will intersect my flow. Oh, but they are both. OK, so let me take this one. So gamma is for the quotient, and I take xx plus zz, where x and z are in R2. Yeah, so this I take x and z as generators. So this is a quotient on the left, yes? And OK, so again, z is in the center. It commutes with x. So x, let me just write x and c commute. So this section is actually a torus, T2. And because, and I'm not in the last one, luckily, oh good. So because I'm assuming that my flow is uniquely ergodic, and we had this lemma before, B is non-zero. So B was the, I don't have it anymore. Omega was A, B, C of x, y, z. OK, so what I want to say that sigma is transverse So, okay. Transverse meaning that I can only do this trick of Poincare map when my sigma, if my flow would lie into sigma, I cannot leave sigma. So I want my flow to cross the section transversally. Okay. Let's finish the... So this is the section. So this is the two-dimensional torus. And then you want to compute the Poincare map. So first you can remark that return times are actually contained in the return time for the flow, for return time. But this is not strictly necessary, but it's kind of guiding you to where you should search for return times. It contains in return times for the linear flow. So this leads you to, so you want, in particular, you want y plus bt to be congruent to y mod 1. On the so I can always project my flow on the linear flow. So remember, my three-dimensional flow also project on this irrational flow. So if I return, no, it's congruent. Yeah, I want to return on this torus. So you want R. So you want the return time has to have the form of k over b, where k is an integer. Okay, so this is, I'm searching for something of the form k over c. And now I claim that actually, so I want to check that 1 over b is a return time. So that actually already 1 over b works. And it cannot be smaller because they have to be multiples of this. Okay, so, and then this is, yeah, again, I never know if maybe I should really not use this form, but okay, I will do this computation and then we'll cover it. So, okay, so this is a small computation. So, using really Lie groups. So I want to compute the following. So I'm taking x of xx plus zz. So this is the starting point in my section. So I take a point in my section, and then I multiply by exp of omega over b. Yeah. So this is my flow phi omega at time 1 over b, right? So I take a point in my section, I flow for time 1 over b, and I want to prove that this is a return time. So I want to prove that this, so I want to see that up to an element in gamma. So and then here I'm going to allow myself to multiply by this. So this you can see from the calculation. So I claim that if I start from the section, I multiply for my flow at time 1 over b, and take everything mod gamma, and mod gamma, I make a precise choice, this element in gamma, I have something which is again in my section. So I want to say that I will again have something which depends only on x and z. So this element, I chose it to cancel the y terms. So okay, now I'm not going to do the whole computation, but I'll just tell you, okay, I don't know, but actually everybody takes some. If you don't take Lie groups, you can forget and just will take the result as a starting point. But so let me recall you Kampfel-Hausdorff formula. So when you have the exponential, so this is recall. So if I want to take ex, ey, so exp, okay, xx, xy, this is equal to exp x plus y plus, and then you have to put 1/2 the commutator. And then you have to put other terms which involve double commutators. But we are in a Heisenberg group, so if I take the commutator of the commutator, 0 in h. So there is this formula for exponential, and now you sit down and remember that z was ax plus by plus cz. And remember the Eisenberg commutation relation and compute. So I think I will not do it. I wrote it actually, but it's okay, doesn't make sense. You compute and you get the following form. You get the exp of x plus a over b x. So I erase this to make some space. Plus z plus x plus c over b plus a over 2bz. So what you found out, okay, you compute and simplify, and you found out that there's nothing with y anymore. So this is, again, in the section. So I came back to my section, because my section is everything which is combination of x and z, and y doesn't have. And not only that, I also computed what is the form of this map. And yeah, I should have changed the board. So you look, and this is exactly a skew product a la Furstenberg. So this is the map. So I have, if I use x and z as coordinates, so this is an f of xz, and the parameters are a over b as alpha, and this one, c over b plus a over 2b. So skew product in x and z. Okay, so this is my Furstenberg skew product. Okay, so from now on, we can forget about, essentially, really, we can forget about Lie groups and forget about this computation, and we will live in the world of skew product and this map. Okay, so maybe an important remark, record it for later. I also want to say, not only we computed the Poincaré map, but the proof also shows us that this 1 over b, it doesn't matter which point x and z I start from. Remark, for every g in sigma, the return time, I called it just Rg, I think. Yes, Rg is constant and equal to 1 over b. Okay, so constant return time. And this is what will kill mixing. We will have to do a break at some point. So I'm not sure if, yeah, maybe can we have 5 minutes now? And then, so then I want to, yeah, we are a bit, yeah, oh, it's okay. So I want to, because I want to define special flow, and then we go to time changes. So we'll see that they are not mixing, and then we'll start really doing the time change mixing. Okay, so this was the beginning, and then the second hour will hopefully will be a bit more involved. But okay, just 5 minutes. Ready to start? Yeah, I have so much to tell you the second hour that we cannot do a long break. Okay, so far we just built background and did this little exercise to find the Poincaré map of the Heisenberg, a uniquely ergodic Heisenberg-Nil flow, which is a Furstenberg skew product. So we found, and again, remember, it's not x and y, but we really want x and z. So z is the central direction, is what becomes the fiber direction in my skew product. And this is going to be very important for the dynamics that we want to do next. Okay, so I wrote here the standard form. I'll take beta is equal to 0. So this is my skew product, x plus alpha, x plus y. Mod 1 I don't write anymore because we are on T2, so it's implicit. And we did the computation, and we found a specific map of this form where the parameters, well, beta here is not 0, but the parameters depend on the generator omega that I chose for my Nil flow. Okay, and now, but this is only a section. It's a map which is a section of my Nil flow. But if I want to reconstruct the whole flow, this is, again, very basic dynamical systems. And it goes back to Poincaré. And OK, the Poincaré section goes back to Poincaré. But there is an inverse construction. You can recover. So I need one more definition. And then we'll start with really the new things. So, and last background notion I want to introduce is if I have a function from T2 to R greater than 0. So now I'm going to draw my torus T2 on the base. And this is X. And this is Y. And I am adding a coordinate. And I call it Z. But apologize, it's not the same Z than before. So our Heisenberg Z is now Y. And the Z is the third coordinate. But that's OK. So this is general definition, nothing to do with Heisenberg. I can build what is called a special flow over my map. So here I have F, and I'm adding. So remember, the picture is that F was a cross section. So I want to add the missing dimension. I want to add the flow direction. So, and I'm. Let me draw. Let me first build an abstract definition. So this is a function. I'm drawing this function C on T2. It's we'll put assumptions. This could also be measurable, or it will be smooth in a second. But any measurable function, say, it's important that it's strictly positive. So, and I'm kind of building some region of space, the region under the graph. So this is called a roof function. It's like the roof of my space. So the ceiling is my torus. This is the roof. And now I have a room where I live. And the space X. No, sorry. Definition. No. So given f roof function, I want to define definition. I want to define what is called a special flow over F under phi. So over the base transformation under the roof function phi, and I will denote it f phi. This is quite standard. So it's f lifted by phi, and it's a flow. So there's a parameter. So let me draw the picture before I write anything. OK, maybe I write the domain is defined on as a space X. Sorry, I'll use X again. This is the graph, the region under the graph. So this is the space of X, Y, Z, such that so X, Y is in T2, and 0 less than Z less than phi of X, Y. So it's this region, this room, and the flow just moves, take a point, and moves vertically up until it hits the ceiling. And when you hit the ceiling, you just move back to the base. So, but if this point was over X, when you move back to the base, you are at f of X and keep moving up. So it's up. And then you glue the top with the bottom through F. So maybe one way to write this is the quotient of the vertical unit speed flow z dot is equal to 1. So you move a unit speed velocity vertically under the identification. So I write it like this. If I have a point, sorry, x, y, and I reach the top, so maybe this x was x, y. So if I am at phi of x, y, so if I have x, y, phi of x, y, I want to glue it to f of x, y. So the image in the base, 0. OK. Is it clear? Have you seen this? Everybody has seen. No, not everybody, but okay. I don't know, there are people in the room, and I know you have a mixed background. Maybe someone will look at this. Maybe someone will look at this recording one day, so it's good to give also some basic definition. But now I finished the basic definition. Okay, so now, so what we, to summarize, so maybe I should say you can use this construction to invert the process, and this is a general fact. Maybe I should have written this. Yeah, maybe I will write it here. Okay, maybe to summarize later. Maybe fact, it's a fact. If I have a flow, this is general. If I have a flow, I don't know, phi r with f has Poincare section. If I find f as a Poincare section and phi as a return time, so if I take phi to be my return time, then the flow is actually isomorphic, metrically isomorphic to the special flow under the roof given by the return time over f Poincare map. So it gives me a way to reconstruct my flow. I'm kind of straightening vertically the flow trajectory. Okay, so to summarize, so we show that HV, no, it was phi VR is isomorphic to special flow over my f. And what was the roof function under constant function equal to 1 over b? You remember the return time that we computed in the exercise was constant. So here's the picture of the dynamical picture of the Eisenberg Nil flow. I'm going to draw a cube. So this is the f is constantly equal to 1 over b. This is my T2, and here I have my f. And here I go up in the cube. It's a parallelogram because it's not, okay. If b is 1 is a cube, I go up, and then I come back. If this was xy, here I come back at f of xy. Good. And I keep doing like this. So this is my Heisenberg flow, Nil flow. And this is how I want to think of the Nil flow for the rest of the day. OK, now we can do time changes. Sorry. And why is it not mixing? Now we see very well that it's not mixing. So take some set, and we can just take parallelogram cube, like a little parallelogram. So this shows corollary, consequence, also consequence. So I promised I'd show you that phi omega r is not mixing. So when I have a special flow with a constant roof, I can take any cube. I don't know, I can take A, for example, some cube, some parallelogram, and flow it under my roof for everything is bounded. It's actually still, yeah, it's bounded in z direction. Maybe something complicated happens in the base, but so there is this stripe, this height. It keeps, nothing happens interesting in the height. So when I flow this up, it comes back all at the same time. And maybe it does something complicated in the base, and it will, because the base is uniquely ergodic. But I'm trapped between two slices of the same distance. Do you see this picture? Do you see this? OK, good. So this is clear that the Heisenberg flow is not mixing. OK, so now the story of time changes come into play. So what I want to show now is that I can time change smoothly and find mixing. So how that? So first I have to be careful because it could be that I time change and I get something which is isomorphic to my original flow. And this is, again, very much studied question in dynamics. So understanding which time changes are trivial or, okay, let me just say, so, okay. So let me recall you mixing time changes is the new title. And now I want to give you some idea of a paper with Arthur Avila and Giovanni Forni and myself. And I must say that this paper has been, it's quite old, now it's maybe 10 years old, but it's been superseded. So here we did Heisenberg. And many years later, we also have a follow-up, which is Avila, Forni, Ravotti. Davide Ravotti, we already mentioned important ones. Davide, Forni, Ravotti, Ulcigrai, and this is maybe appeared last year. So we actually do something for any step 2 Nil Flow. So we were trying for, well, we didn't try very, okay. We were very happy that we, in between, there is also a paper by Ravotti by himself, where he does, Ravotti has a paper where he studies time changes for filiform Nil Flow. Filiform, it's a notion that you can define in terms of the algebra, but actually in this language just means that you are a special flow over a skew product in higher dimension. So you have a Tn, and you have a map like this Furstenberg skew product. It's a higher dimensional version of our paper. OK, so I'm debating. I'm thinking that I might say something about the general case next week, if you want to. But I still think it's much more educational for today to do Heisenberg, because Heisenberg you can see. So you have a nice concrete, this nice concrete coordinate representation. And so the general case is much more abstract, but then it's also based on some kind of induction and on Heisenberg triples into building towers of extensions, each given by a Heisenberg tripole. So it's an inductive argument. The thing is that the new paper is written in the spirit of yesterday's work. So it's done continuously without Poincare recessions, without coordinates. It's done by integration. So it's done by more continuous kind of technique. But I think I like this Heisenberg because you see more what is happening. You see the dynamics better. OK. So we consider what is the notation now? So our flow, why did I write it H? I wrote in my note H because I was with yesterday. OK, but let's just call it phi. So because I don't, so phi r is the Heisenberg Nil flow. Uniquely ergodic Heisenberg Nil flow. And I will use the notation like yesterday. Phi r alpha is the time change. So what is alpha? So actually, you can do the opposite of what we do yesterday. So if I have alpha, if I have tau, I can find alpha. If I can alpha, I can find tau. So you can, which notation I'm using here? Sorry, maybe I will write it like this. Yes, so tau of g, let's use g because x is bad for us. Gt, g is my space, is the integral from 0 to t of alpha of phi s of g in the s. So, yeah, you can, so alpha, sorry, maybe I should have started better. So alpha, I give myself a function from x, my quotient, my Heisenberg manifold, to r plus. So I give myself a positive function, and I use it to build, I integrate it. So, and this just to remember, so that alpha will be the derivative of tau. So if this is smooth, I can do the derivative. If okay, let's not do it. Okay, so if alpha is smooth, this to remember what the notation we were using yesterday, alpha of g will be d tau dt of g0, something like this. And so this is the time change given by this function. And is given by time change given by alpha. So if tau is phi r is given by phi of, and now again we have these two conventions. Someday I have it one way, someday I have it the other way. Actually, I don't know if I even have it. Okay, it doesn't matter. Phi alpha of tau g, I don't know, gt of g is equal phi of alpha. I'm spending too much time because we already see this. Gt, something like tau gt. Okay, it's the time change. So what we prove is essentially that there are many time changes, smooth time changes, which are mixing, and we can explicitly give you. But in order to give you the statement, I have to tell you what is. So warning. So there exists smooth, and smooth I mean alpha is smooth. Smooth time change if alpha is smooth. And there exist smooth time changes which are trivial. And trivial means i.e. phi r and phi r alpha are smoothly conjugated. Smoothly conjugated. So I can find some smooth phi that commutes, which maps intertwines them. Okay, so maybe this is okay. Okay. So let me be much more concrete. So I don't want to make a statement in the language of alpha. I want to move myself to the world of special flows. And here's a dictionary. So I think I prefer the special flow for now. But you can make a statement directly in this time. This was to connect to the notation we had yesterday and also the first day of time change. So the dictionary that one have is the following. So here I have the dictionary between time changes and special flow representation. Special flows. So I think this is nicer to do. Okay, so I have my original Nil flow. So this is H, we call it phi. I dropped the W for now. So phi, this is Heisenberg Nil flow, uniquely ergodic Heisenberg Nil flow. This in the special flow we just did, it's what we called F1 over B. So it's a special flow with a constant time. So special flow under phi, which is constant. So this is my Heisenberg flow. And then I have phi r alpha is the time change. Every time change, you can represent it as a special flow under a modified roof. So if I change my roof, it could be to a new function, So I get phi psi, new special flow, so that the Poincare recession is the same, because the orbits of the flow haven't changed, but the return time has changed, because it will take me longer or shorter to come back. So the return time for a time change is not constant anymore. So, and here, what is the function? Phi of, okay, I'm thinking of the point in the section as in sigma, but is also in x. So this is just the time it takes me to return. So this is the integral from 0 to the return time of g of alpha of phi s of g ts. Okay, sorry. Okay, but the dictionary is not finished, and hopefully I can continue it here, maybe. Let's try. Sometimes I don't need larger boards, I need longer boards, but we have so much space that we can go under and continue the dictionary. Okay, so you should think of time changes as new roofs. And then there is two more I want to change. So it's a smooth time change. And we are going to do a smooth time change just means phi smooth. And that's okay. And now the most important definition. When is a time change trivial? So trivial time change. Trivial means that I get a flow which is conjugated, which is isomorphic to what I already had before. And this you can see very well in the special flow. And it's an exercise that I'm not going to do now, but very instructive to do. You can prove that a new roof will give you something conjugated to the old roof, isomorphic to the previous special flow, if and only if the two roofs differ by what is called the co-boundary. So if I can write my constant b, and my new roof differ by u composed with f minus u. So I can add u composed with f minus u, and this is called co-boundary, where u is a function from T2, T2 to R. So, okay. So this is an exercise. If you try to have two special flows and conjugate them and map one into the other, you will understand that you can find, okay, the conjugacy, this u will enter in the way, okay, maybe just believe me, because I want to go some beyond that. Okay, so if you choose, if you are unlucky and choose a roof of this form, then you get something which doesn't give you anything new. So this is a way to say that time changes are not always interesting. And as I said, we are lucky in parabolic dynamics that actually it's kind of rare to have a trivial time change. And there's plenty of room for finding time changes which are not trivial. But I need to say one thing more. So maybe finish the dictionary so we can talk about smoothly trivial, measurably trivial, or we can talk about smoothly trivial. Did I have a letter for the isomorphism? Okay, so measurably trivial, it's a measurable isomorphism. Smoothly trivial, it's a smooth isomorphism, very different categories. And in this dictionary, measurably trivial means that just u is measurable. And smoothly trivial corresponds to u smooth. Okay, so smoothly trivial time changes when I add a co-boundary for u smooth, and measurably trivial when I use almost. Okay, now a theorem. Theorem, again, Avila for Nil Ulcigrai. And I want to say there are many mixing time changes, many mixing new roofs. But again, it's not as good as yesterday. Yesterday we had every small time change. Today we have to work. It's a lot, but it's not in. Okay, let's see. Theorem. There exists R contained in C infinity of T2. So I'm giving the result in this language of special flows and time changes as new roofs using this dictionary. So I'm thinking of new roofs. So this is the class of roofs. R stays for, maybe I'll use color. So there exists, so in between C infinity function on R2. So this is, there exists a roof, and this is dense. Dense in uniform topology, but I will also need them to be positive. So I will have positive function. And morally, actually, it will be a bit more, but essentially you can think trigonometric polynomials. It will be something like trigonometric polynomials. So, and essentially trigonometric polynomials. And unfortunately, we cannot go beyond that, polynomials. So this question of time changes is very open for, trigonometric polynomials. And there exists tau of f. So tau is what I think of trivial. Tau stands for trivial time changes contained in R. And this has countable dimension and countable codimension. So the trivial ones they will be smoothly trivial. Well, they will be both. Okay, we'll see. So within this dense space, I have countable dimension, countable codimension, such that if my roof belongs to R minus the trivial, and this will, maybe I will call it M of F, sorry. So if I am, so M for mixing, M of F, by definition is R, my space of roofs, minus trivial. So if I'm outside trivial, this is what I think of mixing roof. Yeah, so phi t is mixing. Phi phi is mixing. Okay, so it's not empty because I have countable dimension and countable codimension. Yes?
The vector space big R does not have countable dimension. So how is it possible to find a subspace?
No, it's a infinity function.
What is R?
R is a vector subspace of...
dense enough, trigonometric polynomial.
Dense, so it has infinite dimension.
It has countable dimension.
Yes, there's plenty of... I'll give you examples in a second, so maybe bear with me. I always do this. This is so annoying. Okay, I have to stay to the bottom board for another bit. Is it okay if I erase the dictionary? Because I want to... Okay, so but let me be aware. So if you are in trivial, you have no hope to be mixing. So you need to rule them out. So you need to... So in some sense, it's as good as you can do. And it's important that indeed it's not empty, and it's not empty. But also there is a bit of important point that this trivial time changes. If I had just to write measurably trivial, it would be actually very hard to give any example at all. So there is an important continuation that I write here. Moreover, and this is very important, phi belongs to MF if and only if. So phi in R. So if I know that phi is in my class R of roofs, which is trigonometric polynomial, say, trigonometric polynomials are contained in R. So if I have a trigonometric polynomial and if I want to know if it's mixing, so this is mixing if, so this is trivial, is measurably trivial. So this is measurably isomorphic, but actually it's equivalent to be smoothly trivial. If and only if smoothly trivial. And you will tell me, okay, and so what? Well, so a lot, because measurably trivial would be impossible to characterize, but smoothly trivial has been studied. And actually, I want to explain this next week. It's a small exercise. Katok actually discovered the first example of explicit characterization of obstruction to be. So, okay, I said there are many things which are not smoothly trivial. And this is thanks to Katok in this setting. And then it's been studied by Flaminio, Forni, and others in other parabolic settings. So, sorry. And this smoothly trivial, and this can be characterized. Can be characterized explicitly. And again, this is the first example of invariant distributions. So let me, I have some examples. So you can write actually Fourier series. So we are trigonometric polynomial. So it's actually, we write the coefficient of my trigonometric polynomial, and there are functionals on this trigonometric polynomial that tell me if I'm smoothly trivial or not. So it's, I actually wrote them, but I don't know if it makes sense to write them. And actually what I want to do, maybe I will spend some time next week because it's educational too. It's an important feature of parabolic dynamics. So we'll write what these are next week. But now for today, just to convince you that it's not empty, I have a concrete example. An example of phi, the simplest I have is, so you can check this mostly trivial, and then you can have mixing. So for example, just if you take 2 pi y plus 2. So this is an example of a roof which works for mixing, and it's by Katok computation is not mostly trivial, and then it's no, sorry, phi is in M if and only if not mostly trivial. Sorry, M is the opposite. Sorry, not mostly trivial. Yes, and then I think I wrote a general one. I didn't, but okay, I will write it like time. So phi of x, y. I had one other example, which was cosine. This is a family, 2 pi kx plus y plus sine 2 pi lx plus 3. 3 is just to make it positive, and for any k and l in z. So it's not any trigonometric polynomial. You have some countably many obstructions, but you can find plenty of things which are outside. Yeah, okay. Okay, so is the statement a bit, I know it's not the easiest statement, but somehow that's life, because we have to deal with the fact that there are time changes which don't give you anything new, but there is still room to produce a lot of new things. Make sense? Does it make sense? So now I have the rest. I want to explain some ideas from the proof. And it's nice because, again, we have second example of mixing via shearing that we saw yesterday for horocycle flow. But again, it's a bit good. OK, and I will come back to this. We call it cycle effectiveness criterion, that in this category, smoothly trivial and measurably trivial coincide. And this gives us access to information on what these time changes are. And I must say that this is a big shortcoming of what we can do. So we were very happy that we can prove a result for general Nil flows. And we also proved there that when the time changes are not measurably trivial, we have mixing, but we do not have a characterization of, we do not have this equivalence of smoothly trivial and measurably trivial being equivalent. And therefore, we do not have explicit. I cannot, in the general case, give you examples. So it's a bit a drawback. And also, as I said, okay, maybe I say it now. And maybe I should say, Okay, I'll say it now because. Okay, so and Kanigovsky and Forney in a special case. So when the rotation number is bounded type, so Kanigovsky and Forney under the assumption that alpha is bounded type, so it has, this is measure 0, bounded continuous fractions. So measure 0, they actually have some result about quantitative mixing. So mixing with speed, polynomial, okay, quantitative mixing. But unfortunately, it's only for measure 0 set of alpha. Okay, so ideas. Let's see where we start. So idea of proof. So I want to start from the skew product, from the special flow. And I'm now drawing imagine this cosine of y would already be enough just to have oscillation at least in the y. So this is x, and this is y. But remember, y was z in the Nil flow. So it's the central direction. So this is the central direction. And here we have isometric action. So here my Nil flow acts isometrically. So in this direction, when I move fiber to fiber, we saw before, this is the skew product, Furstenberg skew product. So here, if I have an interval in this z direction, it will never grow. It will project always to something of the same. So I cannot touch f. F I cannot change. F I'm given. I can only play with the roof. So f is given, and here I'm isometric. So how am I going to mix something? So the idea is actually to find shearing. So let's start with this, and then I'll explain you how. So idea of proof. So first of all, I will write mixing via shearing that we learned yesterday about. And the idea is that, you remember yesterday we said, okay, I can maybe chop some set into small arcs and hope that these arcs shear in the flow direction. So when I push my set, each of these arcs shear and become a long flow trajectory. And if the flow is uniquely ergodic, this trajectory equidistributes. And so this is shearing goes from equidistribution. I can get mixing via shearing. And this is exactly what we are going to do. And what is the direction? So we are going to consider arcs, so intervals in this case, intervals. Let me call it gamma, okay, in y direction, in the y fiber. So in fiber y, we will, and here not all intervals will be good, we'll see in a second. We will have to throw some bad intervals. They will not be stretched everywhere, but we'll have to throw some small measure set. Consider intervals in the fiber. And let me spoil the picture, then I'll explain where it comes. So we'll find many that shear in the flow direction. The flow direction now is z. So which is z in this picture, not z in the, so this is z here. So what am I going to find is that I can find an interval here that gamma. So, and if I plot phi t of gamma for t very big, this will start shearing. So now I will draw phi t of gamma. It will be something very sheared. So when I shear a lot, I have time to actually go many times around, up and down. So yeah, so how do I say? So if I have an interval and this, the projection is, so if this is my gamma and this is my phi t of gamma, so if it shears, it becomes infinitely long. So when I put it in my room, I have to quotient by the ceiling many times. Is it okay? So this is one single interval. When it shears a lot, so this will, I don't know, this is A and this is B. So this would be phi t of A. And my single interval goes here, then it's glued to something else, then it's glued to something else, then it's glued to something else. Okay, and then it stops, and here I find phi t of B. You see, so it's a single. So in the y direction, I haven't gained anything, but in the vertical direction, I have stretched a lot. And so this is how a long orbit of the vertical flow, of my special flow, is just straight segments, union of straight segments. And my sheared segment is not really vertical, but almost. So it shadows an orbit of the flow. Does the picture make sense for people? Yes? So this is a preview of what's going to happen. So if I find this with some good quantitative estimates on, well, not quantitative, but okay, I have to really show that this is the picture in the sense that I grow and that I become more and more straight. Then, so there is some distortion. You don't want a wiggly, you don't want a long, but so you have to control. But if I can see this, and I will try to convince you where it comes from here I can conclude, like we explained yesterday, and I will not say much more. From here, one can conclude, I can use some Fubini if you want. And in this paper, we really do. We don't do, because we really write by hand. If I have any a set, I chop it in these little arcs, and each of these little arcs individually equidistribute, use Fubini, and prove mixing, deduce mixing. And this is kind of long and technical. We really build partitions and so and so. So now I want to convince you that this is the picture that we see. And once we see this picture, we'll be happy that we can conclude the mixing via shear. So why do I see that? And how do I estimate shearing? How do I prove that there is shearing? Okay. And by the way, this is very important. I'll anticipate it also. So if you get lost, you will at least remember the picture. If I take another interval now, not the same, yesterday we had the same shear for every point. The horocycle was shearing in the same way. Here, if I change interval, it might be that the other interval shears in the opposite direction. And it will really happen. So there will be some intervals which shear in the opposite direction. And there are also bad intervals. There are some bad intervals which don't shear at all. So the space is much more complicated. So some parts that shear in one direction, some parts that shear in the other direction, and some pieces you have to throw because you don't shear. Okay? Okay, let's try. So let's try to explain. So now I have to go back to special flow. So we need an equation. So maybe let me do something. Let me change board so that I don't run out of space. And this picture we keep it on top because it's nice. Good. Okay. So I have to explain. I have to write a formula for this is classical for how the special flow acts, because so far I just described it in words. So special flow dynamics. Maybe let me redraw the picture. So how do you define? So imagine that you want to flow for time t. So where am I after time t? So I have to count how many times I go up to the top and down. So I start flowing, and then I come back. So I want to know how many times in time t I go up and down, and to know where I am after time t. So let's define, so I need a formula. So given x and y, let and t to compute f phi t of xy, explicitly, I need to know let, and first of all, I want Birkhoff sum. So I need to measure how much I travel. So let me write Fn of xy. This is the Birkhoff sum. I want to sum the values of the function over the base dynamics. This is the strakes that I do. This is the sum from 0 to n minus 1 of phi of fk of xy. So the first time I do f of xy, the second time I do phi of xy, the second time I do phi of f of x, the third time I do phi of f square of x. So this I'm summing. It's just my Birkhoff sum. And let n t of xy, this is how many discrete iterations I do in time t. This is the sum, it's the max of n such that phi, I'm so sorry, I wrote it wrong. I'm so sorry. This is not phi, but it's phi. So this is a function which I'm summing. These are called Birkhoff sum. It's like a discrete version of the Birkhoff integrals. Birkhoff sum, sorry. So this is the max such that phi xy is less than t. So this is the last time in time t that I am below the roof. This is very standard in dynamics, but OK. And then f phi of xy. So in the this number is exactly how many strakes I can do up to time t. So at time t, I have hit the base n times. So in the base, I will be at f power nt xy of xy. So this is where I am in the base. And the time at the height is what is left of t when I remove phi and t. OK, so I don't know if I could convince you. Maybe I was too fast. But OK. So this is just understanding how the special flow works. So if it was too fast, you can meditate on it, or you can ask me later. I'm happy to re-explain. But this is just a starting point. It's just a formula for the special flow. I haven't done anything which is not in a textbook in ergodic theory. But so what I want to do now, I want to understand what happens of my y. And I am running a bit out of time. So let me recall. So I want to understand the shear. So I want to take some kind of derivative in the y direction to understand how the profile, if I push, I want to know if I move in the y direction, how this, I want to know what happens, how this changes in y. So how does it change in y? How does it change in y? And to know how it changes in y, so I have two remarks. One, we already this is phi is an isometry in y. We already said that in y direction. y direction, acts isometrically. Two things in the fiber. So this is y goes to f of something x plus y. So I'm just shifting by x. And the remark 2 is that, I forgot something important. Okay. I'm trying to think what I do in terms of time. I don't know if I should break some part to next week. Maybe not ideal. Okay, that's fine. I'll try to do d phi in dy. So, okay, maybe that's okay. I don't need remark 2 yet. So, because it's an isometry, if I want to do d phi n in dy, so these are Birkhoff sums. So they are sums of this form. And in y, I have isometry. So I can do chain rule if you want. It's a sum. If I take the derivative in y, this part has derivative 1. The partial derivative is y. So what I want to say that when I do remark 1 implies that these are Birkhoff sums of the derivative. So these are, I take the derivative in, so maybe d phi in y n. Yeah, that's what I want to write. So the derivative of the sum is the sum of the derivatives because of remark 1. So, okay, and now so I want to show that this thing grow. So I want to show that for these segments for many segments in the y direction, this partial derivative, so this partial derivative you should think of as the shear. This is the shear of the y segment. So this is the shear in y direction. Okay, and I want to show that it's big. So here I want to get to the conclusion. So I'll try to fit it. Maybe I'll take 2 minutes more to say something. And if you want, I can go back to explain more, but okay. I want to come back to this cocycle effectiveness next week, but it's a different story. So what are the mixing proofs that we are going to take? That's what I forgot to tell you, and I'll tell you now. So what is M of F? So R of F, take R to be, let's just take for simplicity trigonometric polynomials. In reality, I just need a bit less. I just need trigonometric polynomials in y direction and maybe some continuity or some. But let's, for simplicity, take just trigonometric polynomials on T2 and then adjust intersecting with positive because I want a roof. So I want to, we had the example before, some cosine, sine, and I make them, I add something to make them positive. And what is MF? MF, I'm going to look at, let me find. I want to, basically, if I have phi in R, such that if I look at, we call it bad notation, we call it phi, which is phi minus the integral of phi in, okay. We remove I want to remove the mean in each fiber. So phi, small phi of xy is big phi of xy, and I want to make it mean 0 in each fiber, minus the integral of phi xy in dy from 0 to 1. So this is the mean 0 in the fiber, in each fiber. So we want this, and we want to ask that this is not a measurable coboundary. Okay, so again, this would be completely abstract condition if not for this cocycle effectiveness that tells me that it's actually equivalent to, a posteriori, it's equivalent to smooth coboundary, and then it becomes something checkable for trigonometric polynomials, as I'll try to convince you next week. Okay, and now I want to take two things. Okay, so, and now, by the way, this is where I remark that when I remove the mean, I'm just centering the function. So d phi, this was remark 2, d phi in dy is it the same letter? Big phi, and maybe I should have used a different letter not to confuse you everything. So let's call it phi, so we don't get confused. It's the one which means 0, I change letter. Var phi in, what is that? Okay, sorry. Okay, so this is just I differ by a constant in each fiber, so they are the same. Okay, so two things, so two steps. Step 1, that I don't want to explain, but I didn't plan to explain either. Step 1 is that not measurable coboundary implies the following, implies that there is some growth. So it implies that for every constant greater than 1, or for every constant, Lebesgue measure of points such that the sums of phi, Birkhoff sums of phi, are greater than c. So I fix a large constant, and these sums will be greater than c for most points. The Lebesgue measure of this set will go to 1 as n goes to infinity. Okay. So this step is not obvious. It's again, it's I want to highlight. Yeah, maybe okay. So maybe I can say one thing. So I can say there is a general fact that when you have something which is not a measurable coboundary, you can get some average. So if I say zero average of this quantity, you can get for growing for free, because it's in some sense related to Furstenberg, and I will write a key word for the expert. It's Gottschalk-Hedlund. Gottschalk, did I spell it correctly, Mark? No, how is Gottschalk? S-C-H. Eh? S-C-H. Gottschalk. Okay, Gottschalk-Hedlund. Gottschalk-Hedlund. In general, it will give you some average version, and then I will write another keyword, some decoupling. So it's an interesting part of the paper, but I don't want to do it in any case today, and you're happy to ask me more separately if you want. Okay, but this is some abstract ergodic theory, and add some feature of the Nil Flow that somehow the dynamics of the Nil Flow, the skew product map. Okay, so but you get a growth of, I want to highlight the second step to explain trigonometric polynomial and conclude. So somehow in norm, these functions are growing. The second step is what I want to say because it uses trigonometric polynomials. So if I have a trigonometric polynomial and the norm is large, so here I looked at phi n is a trigonometric polynomial, and it's actually a polynomial of bounded degree. So that's why it's also important to work in this central direction, in this y direction, because the polynomial, trigonometric polynomial doesn't grow in degree. So if I have a trigonometric polynomial with large norm, the derivative is also large. So yeah. So what I want to say, we can also prove that the Lebesgue measure of xy such that d phi n in dy is greater than c goes to 1 as n tends to infinity. So I actually have a lot of shear. And I finish with a picture. And so what should you imagine? Just to understand that the stretch is really not uniform in this case. So what you should picture? So I'm picturing a y fiber. So this is the y direction. And I want to picture, so let me draw it like this. This is x times 0, 1. And I'm drawing the graph of, say, the function. I'm drawing phi as a function, phi n as a function of y. This is a trigonometric polynomial with a very large norm. So it looks something like this. It's oscillating. And so it has large derivative on a lot of, but the derivative can be positive or negative. But of course, there are some bad intervals where it's flat. So there are some intervals. So the flat intervals, flat intervals, there are flat intervals. So this is where there is no stretch. And this is what I have to throw away. So this is the oscillation. So the oscillation is a bit positive, a bit negative, but it can be flat. And the last ingredient is also some estimate. So it's a trigonometric polynomial, so we also use it. So maybe last ingredient. So you have some, you want to estimate these level sets. So you have some polynomial bound on level sets of a trigonometric polynomial, which is uniform in the degree, up to normalize them by a constant to make them normal. Maybe I think I said enough. So, but okay. So this is just to say that we use trigonometric polynomial in various places. But what's important, I hope I got you the idea. So this time change makes shear, gives shear in the y direction, but this shear is very inhomogeneous. So some parts is one direction, some parts is the other, and parts I have to throw away because they are not sheared, but they're small in measure. And the more that I grow, the more I have oscillation, and the smaller the intervals that I have to throw away. And that's enough to get mixing via shearing going. But you see, it's quite different than the mixing via shearing we saw yesterday. OK, so I finished for today. And maybe I wanted to say next week. So I would like to do, so I want eventually to go back to shearing in an improved form, in the form of Ratner property, and say a few more things that you can get out of shearing when you make it more quantitative. And I also would like to go back to this general Nil flows and give you a sketch of the general case. But before I will do all of this, that I will do at the end of the week, the next class, I would like to dedicate it a bit to these other two phenomena that we haven't talked about. And one is actually renormalization, so how renormalization is important in the study of parabolic dynamics, and try to explain deviations of ergodic averages. Maybe I will go to the case of surfaces and even linear flows of surfaces there, because I think I'll do another thing simple, but which gives a new ingredient in parabolic dynamics. And I also want to explain this Katok obstruction for the Skew product, because I think there are two fundamental ideas in parabolic dynamics. So I have two simple examples, this renormalization for linear flows and polynomial deviation, and this Katok will be new and self-consistent. And then in the last classes, I will go back to strengthening what we saw yesterday and today towards general Nil flows and towards Ratner property of shearing and the application, which are more disjointness and multiple mixing. OK, good. Thank you. Thanks a lot for coming, for the attention.